Welcome to part 3 of our video series in support of hypothesis testing. In this video, we are going to discuss use of the z-distribution for performing inference on the difference in two means from independent populations. I'm Renee Clark from the Swanson School of Engineering at the University of Pittsburgh. Okay, so let's talk first about the case in which our population variances are known. So sigma 1 squared known and sigma 2 squared known. Okay, so again, we're performing inference on the difference in two means from independent populations. Okay, now when our sigmas are known, we can use z, correct? Because z involves sigmas in the denominator. However, in order to use z, the quantity that I have circled here must be normally distributed in order to transform that quantity to a z random variable. So, in order to use z, x1 bar less x2 bar must be normally distributed. Okay, when will that be the case? Okay, the first possibility is that each of your sample sizes, n1 and n2 out of the population, are each greater than or equal to 30, okay? In which case the central limit theorem applies, okay? The second possibility is when each of your underlying populations is normally distributed, okay? So x1 normally distributed and x2 normally distributed, okay? So if either of those two possibilities or both is true, okay, that means then x1 bar normally distributed and x2 bar normally distributed, okay? Now, if we know that this is the case, that each of those sample averages is normally distributed, then the difference in the sample averages will be normally distributed, because a linear combination of normally distributed random variables is also normally distributed. Remember, we learned that earlier, right? So in other words, if we know x1 bar normal, x2 bar normal, okay, then this quantity here is a linear combination of each of these two random variables, okay? And if they're normal, the linear combination will be normal. Okay, let's go back up to the test statistic, okay? How do we actually calculate the z test statistic when we're doing inference on the difference in two means? Well, we subtract off from x1 bar less x2 bar, we subtract off its expected value. Okay? And we'll recall from earlier that the expected value of the difference in the two means is simply mu1 less mu2. Okay? In the denominator, we have the standard deviation of x1 bar less x2 bar. We'll recall earlier that this is the equation for the variance of x1 bar less x2 bar. Sigma 1 squared over n1 plus sigma 2 squared over n2. To get the standard deviation in the denominator, we simply take the square root of the variance to get the standard deviation. Okay? That is how you calculate the z test statistic in this case. Okay, so same case, our sigmas are known. Okay? But now we want to go through the proof by contradiction aspect. Okay, now when you are doing inference on two means, this is often what your null and alternative hypothesis looks like. Normally we say or hypothesize that mu1 equals mu2 versus the alternative that mu1 not equal to mu2. Okay? Now, if we are hypothesizing that mu1 is mu2, another way to write that is that mu1 minus mu2 is 0, meaning there's no difference between them. And if you look at it algebraically, if you simply subtract mu2 from both sides, you'll get mu1 minus mu2 on the left, 0 on the right. Okay. We call this difference d sub 0. This is our hypothesized difference. Now, typically when we're doing hypothesis tests, typically the hypothesized difference is 0 because oftentimes this is what we're testing, that there's no difference in the means. However, the hypothesized difference can be non-zero if you're hypothesizing up front that there is a difference, okay? But in this case, there is no difference, okay? So we now want to proceed with our proof by contradiction because that's how hypothesis tests proceed. What do we do in that case? Remember, proof by contradiction involves, in order to try to prove the alternative, you have to assume the null to be true. Well, if the null is true, there is no difference in mu1 and mu2, okay? So that's why we insert a hypothesized difference of 0 into this test statistic. And when we do, that term vanishes. It goes to 0. But of course, in the denominator, we still have our standard deviation of x1 bar less x2 bar of sigma 1 squared over n1 plus sigma 2 squared over n2, the square root thereof. Let's now talk about the case of our population variances unknown, okay, or our sigma 1 squared and sigma 2 squared unknown. We're still doing inference on the difference in two means, but population variance is unknown. However, we have the advantage that our sample sizes are each large, okay? Well, in that case, we can still use z, okay, as our test statistic, or we can use the z distribution. The reason for that is when our sample sizes are large, okay, you'll recall that our sample standard deviation is a very good estimate of our population standard deviation, okay? That would obviously hold for both populations, okay? Or another way to write this, S1 squared, good estimator for sigma 1 squared, S2 squared, good estimator for sigma 2 squared, okay? So with those S's being good estimators for the sigma, that means that in our variance equation for the difference in the sample means, we can simply replace the sigmas with their corresponding S's, okay? And so that's why in the denominator, you see the S's instead of the sigmas, okay? And of course, with our sample sizes large, we know that that quantity will be normally distributed by the central limit theorem. By application of the central limit theorem, and then also knowing that a linear combination of normally distributed random variables is also normal. Okay. This is often what our null and alternative hypotheses look like when you are performing inference on the difference in two means. We typically hypothesize no difference in those two means. So that another way of saying that is that mu1 less mu2 is 0. That's our hypothesized difference, in this case of a 0. To proceed by proof by contradiction, that 0 gets inserted into the test statistic for mu1 minus mu2. Of course, that term vanishes to 0 because we're hypothesizing no difference. Wish to thank the National Science Foundation under Grant 233-5802 for supporting our work. Thank you for watching.